Hello, I'm Mike Dodds and I'm a principal scientist at Galois. We're a research consultancy with a focus on high assurance systems, formal verification and security. Today I'm going to talk about distributed protocol verification and in particular some work we've been doing formally verifying the Stellar blockchain protocol. This is a brand new protocol that's already been deployed in production and we're working with the Stellar Foundation on verifying core correctness properties of their protocol. We believe this is the first mechanized proof of both safety and LTL liveness properties for a deployed consensus protocol of this kind. The tool we've been using for Stellar and other distributed systems is called Ivy, which was mainly developed by Ken McMillan at Microsoft Research. I'm going to explain how we applied Ivy to the Stellar protocol and why we see the Ivy philosophy as a path forward in verifying distributed systems. Before I go further, let me also say that this project is joint work with Giuliano Losa, my colleague at Galois. Distributed systems verification has been a topic in computer science since at least the 1980s, but we're still surprisingly far from being able to routinely verify production distributed systems. That's a problem because more and more systems rely on distributed protocols. Here are 4 characteristics I'm particularly interested in when I talk about distributed systems. First, control and computation is distributed amongst many asynchronous nodes. Also, the nodes have to collaborate to achieve a shared objective. As a result, the most important correctness properties concern the whole system, not the behavior of individual nodes, and the node and network may be faulty or even adversarial. Cloud computing platforms are an obvious example of distributed systems in production. Reliability and security are key concerns for a cloud system. And in fact, cloud-scale businesses like Amazon and Google have been amongst the most enthusiastic adopters of formal methods. More and more data is moving to the cloud, and that includes data that's private, commercially confidential, or even classified. A modern cloud platform involves many interlocking distributed protocols working in concert to achieve consistency, availability, and security goals. Cloud services are inherently subject to failures of the nodes and network, as well as malicious behavior from within and outside the cloud. But we can also interpret other application domains through the lens of distributed systems. Cyber-physical systems have many of the same characteristics, including asynchronous communication, collaboration between nodes at both the software and physical level, and faulty and malicious participants in the system. We might imagine a system including semi-independent drones, ground units, and multiple points of control, some of which may have been corrupted. In all these cases, we want to be confident that these systems meet their goals. Unfortunately, history shows that people consistently fail to get distributed protocol designs right. Perhaps only cryptographic systems are more consistently vulnerable to design errors. That suggests, just like cryptographic systems, we need formal methods tools for distributed protocols. At Galois, the work we've been doing has focused on blockchain protocols. Blockchains are a great place to start solving problems in distributed systems verification, even if your objective is to verify cloud systems, cyber-physical systems, or something else. The first reason for this is that blockchain research is going through a kind of Cambrian explosion of protocol designs. Blockchain researchers are rapidly designing and then deploying a broad range of new protocols, and these new protocols are intended to solve the exact problems we see in other kinds of modern distributed systems. The core aim is to establish trust at scale in an adversarial environment. The second reason is that the assurance problems in blockchain are very severe. In part, that's because blockchain applications inherently operate in an adversarial environment. There's a limitless supply of smart people who will enthusiastically steal your money and exfiltrate your data if you make a mistake with your protocol. But it's also because there's currently a very short path from designing a new protocol to deploying it in practice. While more standard protocols such as Paxos have been studied for many years, it's common for blockchains to design software and protocols together. Perhaps the most important reason to focus on blockchain is that blockchain companies are willing to pay for assurance so long as it works. To state the obvious, formal methods aren't the only way to assure systems. In fact, they're a tiny niche compared to testing-based methods. If we're going to compete with other assurance approaches, we have to achieve good trade-offs in terms of time and effort versus assurance gains. Commercial blockchain projects can be a proving ground where we find out exactly what actually works in practice. With all that said, let's take a look at the target for this verification project, the Stellar Consensus Protocol, SCP. I'm not going to explain the protocol in detail, but I want to give a flavor of the problems we're tackling. SCP is a consensus protocol. Its purpose is to allow distributed processes to agree on a common result of computation. Consensus is a classic problem in distributed systems, and in blockchain it's used to reach agreement about the outcome of each transaction. For example, in a cryptocurrency, the participants have to agree who owns what quantity of the currency. The aim in each round of the consensus protocol is simple. Each participant proposes a new block representing the result of a set of transactions. In a cryptocurrency, these transactions might be the transfers of currency between participants. Then, through the consensus protocol, all of the participants agree which block is chosen, and therefore what set of transactions take effect. Bitcoin and Ethereum are open blockchains, meaning that anyone can participate in the protocol. This creates a problem when trying to establish agreement, because malicious parties can attempt to corrupt the consensus protocol by creating thousands of fake participants. Other blockchains solve this problem by either forcing participants to perform difficult computations, this is called proof of work, or allowing them to vote based on their current ownership of resources, this is called proof of stake. The idea is to raise the cost of participation to the point where a malicious party can't easily flood the system. The Stellar Consensus Protocol takes a different approach. The SCP chain is open, but each participant can decide which parties it trusts. Parties that are mutually trusting can come to an agreement amongst themselves using the protocol. Most importantly, each participant can have a different idea of which nodes are trusted. The reason for this approach is that the Stellar network is designed for exchanging digitized real-world assets. Most participants are expected to have recognized identities and real-world trust relationships. You can imagine this would be true for financial institutions, for example. These identities are difficult to generate, which avoids the problem where malicious parties flood the network. As a result of this design, SCP allows different parties to come to different conclusions. There need not be a global consensus between all the participants in the protocol. The hypothesis is that the real economy is connected enough that the Stellar network will remain a single consistent unit, despite failures, misconfigurations, and attacks. We can draw an analogy with the internet, which remains a single entity despite a lack of a single centralized authority. To me, what's most interesting about SCP is that it embodies with a flexible notion of trust between the parties. We can imagine this being true in cloud environments or cyber-physical systems just as much as it is on blockchain. Let me explain the SCP model in a little more detail. Each node in the Stellar network broadcasts a set of slices where each slice is a set of nodes. Intuitively, each slice represents a group that together the nodes trust. A node will accept some new information on the network if all nodes in one of its slices agree that the information is correct. A quorum is a set of nodes that can potentially reach agreement. In SCP, a quorum for node n is some set of nodes Q such that n has a slice included in Q, and each member of Q also has a slice included in Q. In other words, a quorum is a set of nodes that satisfies the agreement requirements of all nodes in the set. The result of this definition is that each node forms its own personal quorums based on its own slices and the slices of the nodes it's aware of. This leads to a patchwork notion of trust that emerges between nodes in the network. This protocol has some unusual properties compared to traditional consensus algorithms like Paxos or Raft. First, quorums are not global to the system. Each node has its own view of its own quorums. Second, the quorums of a node depend on the slices that other nodes declare. A misbehaving node can influence the other quorums of well-behaved nodes. And third, some nodes may not share enough trust to reach consensus. It's even possible there may be consensus islands, a group of nodes that never converge on common agreement. Each of these properties increase the number of possible situations of the protocol and make it more difficult to formally verify. The Stellar Consensus Protocol is designed to provide two properties for sets of mutually trusting nodes. These are the two properties that we want to formally prove. First, when a collection of nodes believe they've reached an agreement, a quorum, it's impossible for two nodes to disagree about the decision. This is known as a safety property. Second, under some reasonable assumptions about the network and the structure of the quorums, a set of nodes can eventually reach an agreement. This is a liveness property. We also have two requirements that play into our choice of tool. The first is we want to verify these properties for networks of any size and for executions of any length. This is because we don't know what size the system will reach in practice. As a result, we can't just apply bounded model checking to the problem. For this type of protocol, model checking will only discover errors that occur at trivial sizes. This is because the possibility of malicious behavior exacerbates the state space explosion problem. The second requirement is that we need tools that can help us be productive while doing proofs. By productivity, I mean the level of effort it takes to achieve a particular level of confidence in a system. Productivity isn't much talked about in formal methods. However, I'd argue that it's a key measure of how useful a formal methods tool is in production. As I mentioned above, formal methods tools are only one kind of assurance tool that's available. The main resource that we're competing for is time, the time for experts to construct a proof, and time for developers to understand the results. To me, that means we don't need tools that are maximally powerful, but rather tools that make good trade-offs. In particular, we need tools that help experts express their ideas concisely while providing rich automation and feedback during the proof process. The main tool that we've been using to solve these problems is Ivy, which was developed by Ken McMillan at Microsoft Research. I don't know whether Ken thinks of it this way, but to me, Ivy seems to be a trade-off between two different types of formal verification tool. One kind of tool that's often used for distributed systems are modeling languages such as TLA+ and Alloy. These tools define high-level languages in which a system is expressed as nodes and relations between nodes. They have the advantage that it's easy to develop and experiment with the system design, and they're generally equipped with a model checker, meaning it's easy to verify small instances of the design. And in fact, TLA+ and Alloy are increasingly popular in production, in part due to good books such as Hillel Wayne's Practical TLA+. The disadvantage of these tools is that while it's easy to be sure the system behaves as expected for bounded numbers of nodes, it's difficult or impossible to verify a system at all sizes. That's a big problem for distributed systems, where exercising the most complex behaviors can involve dozens of nodes or interactions that are hundreds of steps deep. From a formal verification point of view, the problem is that systems like Alloy and TLA+ have limited support for reasoning about logical quantifiers. To fix this problem, we might reach for a proof assistant like Coq or Isabelle. These tools provide an enormous amount of expressive power. Key results in formal verification, such as the SEL4 and CompCert projects, have been accomplished using theorem provers, and then even been used to prove deep mathematical results like the four-color map theorem. But a big disadvantage for these tools is that even small proof tasks can be extremely expensive in terms of expert effort. Headline projects such as SEL4 and CompCert have been accomplished by world expert teams by dint of many person-years of hard graft. The root of this problem is that the tools are both highly expressive and also meticulous about the details of each proof step, and the space of possible proofs is so large that it's hard to design effective automation that can help proof engineers be productive. My interpretation of Ivy is that it tries to take a middle path between these two types of tool. To help proof engineers be productive, we need to be able to automate as much reasoning as possible. To do this, we can use logical solvers like Z3, but for automation to be effective in large proofs, we need it to have the following properties. First, predictability. We should be able to reduce proofs to automated lemmas because we can reasonably predict solver performance. Second, stability, or we might call this continuity. Small irrelevant changes do not greatly impact solver performance. And third, transparency. Failures have understandable explanations, especially if they're due to errors in the proof. Ivy's hypothesis is that predictability, stability, and transparency lead to productivity for proof engineers. If we try to automate a proof step using a solver like Z3, these properties depend on exactly what shape the formula takes. In fact, these properties won't hold in general for even quite simple logical queries. So Ivy's answer is to constrain the proofs so that these properties are guaranteed to hold. The way it does this is to ensure that every formula has a property called decidability. A logic is decidable if there's an algorithm that can determine the truth of any formula. Intuitively, this means for any given formula, a solver like Z3 will always answer whether it's true, or if not, return a counterexample explaining why not. So decidability helps with all three goals. Solver performance is predictable, performance stays stable so long as all queries are decidable, and failures are transparent because the solver generates a counterexample that explains the problem. It's important to point out that this severely limits the kind of proofs that can be written. Even first-order logic, consisting of universal and existential quantifiers and standard logical connectives, is undecidable. So the biggest surprise from recent research on Ivy is that many important proofs can still be expressed using a decidable proof language. That's great news, because it means that many more systems can be effectively verified. The complete proof of the Stellar Consensus Protocol is too large to explain in detail in this talk. But in fact, Ivy's proof language is simple enough that I can go through a small example in a lot of detail. The one I'm going to talk about is the Toy Agreement Protocol, a very simple consensus algorithm. This is the algorithm. First, each node non-deterministically chooses and broadcasts a value. Then, nodes reach an agreement if some strict majority picks the same value. Now obviously this algorithm won't necessarily result in choosing a value, but it does satisfy a safety and aliveness property. First, a safety property. No two nodes can decide on a different value. Also, a liveness property. If messages are reliably delivered and a strict majority proposes the same value, all nodes reach the same decision. I'll use this very simple consensus algorithm to explain how Ivy works. The first thing we have to do in Ivy is to define the domain. These are the elements of the model that won't change as a result of the actions in the protocol. The three basic types in the protocol are the nodes, values, and quorums. The meaning of the first two should be obvious, but quorum might seem a little confusing. Rather than represent each node's quorums directly as sets, we represent them as entities. The next line in the domain model makes this clearer. This is the static relation member, which ties each node to a set of quorums. Finally, the axiom is_quorum says that any pair of quorums has to overlap on some node. Intuitively, we can interpret quorums as all the sets that comprise a majority of the nodes. But in fact, this axiom is much weaker and doesn't, for example, say that a node has to be part of a quorum, or in fact that there have to be any quorums at all. This is a property of quorums that suffices to verify the algorithm, but that can also be encoded into decidable logic. In order to make sure that reasoning in Ivy is decidable, every part of the model has to be expressed in decidable logic. I'll explain a decidable fragment called EPR, but actually Ivy supports any decidable logic that's supported by Z3. And in our stellar proofs, we use a slightly more expressive logic called FAU. EPR is a very restricted language of properties. We have the constructs of propositional logic. These are the normal logical operators we might use in a conditional branch. For example, logical AND or negation and implication. We also have universal and existential quantification, but only over individual elements, not over sets and relations. We don't have any built-in theories, so we don't have arithmetic, bit vectors, arrays, or any of the more powerful notions we get in SMT solvers like Z3. And EPR restricts how quantifiers can alternate between universal and existential in a formula. If we follow these rules, the logical terms we generate are guaranteed to be decidable. These restrictions make it clearer why we wrote the domain model in the way that we did. We encoded the notion of a quorum as a type, not a set. We can't quantify over a set of nodes making up a quorum, but we can create an object that represents the set. We don't have arithmetic, so we can't use cardinality of the set to define the majority, but we can define majorities as having common overlapping elements. This gives an idea of the kinds of encodings we need to make the Ivy approach work. The main work of writing a proof in Ivy is encoding the notions we want into decidable logic. If we're lucky, these notions fit naturally, but if not, we have to do some work. Here's the rest of the Ivy model of the toy agreement protocol. First, we represent the state of the protocol as relations that can be modified as the protocol executes. Here, the proposed relation represents a node choosing the value to propose, and the receive relation represents that a node has received a proposed value. The decision relation represents a node deciding on a particular value. We also initialize all these relations to empty. At the start of the protocol, there aren't any proposals, received messages, or decisions. Now we come to modeling the protocol itself. Ivy defines a small language of actions representing transitions in the protocol. One thing to note is that each action can take place at any time, unless we add extra conditions saying when it can fire, and action parameters can take any value of the appropriate type. For example, this means that we don't need to explicitly choose the node or value to be proposed. Ivy does this implicitly. The propose action begins with an assume that guards when the action can fire. Ivy interprets capitalized variables as universally quantified, so we can read this guard as ensuring that the node n hasn't proposed any previously proposed value. It then updates the proposal relation to record the value it chose. The result is that each node can propose at most one value, and it will pick that value non-deterministically out of the set of possible values. The receive action begins with a guard that ensures it only fires once the appropriate value has been proposed by some other node. It updates the received relation to record that the message arrived at the node. Then the action checks whether the set of nodes from which messages have been received form a quorum. If this is so, the node indicates that it's decided on a value by updating the decision relation. Finally, we specify the desired safety property. This states that if two nodes make a decision, they better decide on the same value. One thing to note is that, just as with the domain model, the transition relation and the safety property have to be specified in decidable logic. We proved the safety of a distributed system in IV by defining an inductive invariant. This also has to be defined in decidable logic. An invariant I is inductive if the initial state in the system satisfies I, and any transition from a state that satisfies I also reaches a state that satisfies I. If an invariant is inductive, it holds for all the possible states that can be reached from the initial state, and because we haven't specified the number of elements in the model, it also holds for any possible number of nodes, values, and quorums. Up until this point, most of the modeling that I've shown could be expressed in lightweight languages such as Allo and TLA+, but this is the point where IV is able to reach beyond those systems and prove properties about unbounded executions and unbounded numbers of elements in the model. The invariant for the toy agreement protocol states three properties. First, a node can only propose a single value. This holds because of the guard and the propose action. Second, if a node receives a proposal, it must have been proposed by some node. This holds because of the guard and the receive action. Third, if a node made a decision, the chosen value must have been part of some quorum. It's the third property that lets us prove the safety property. If two nodes make a decision, then each node must have an identified quorum, but any two quorums must have a common member, and each node can only propose a single value, so it must be true that the nodes decided on the same value. Here's a diagram of the verification process in IV. The key here is that at each step of verifying a system, IV provides informative outputs. The ingredients used to make a proof are the transition system, the property to check, and the candidate's inductive invariants. These all feed into IV's generator, which constructs a set of verification conditions. If these conditions hold, then the invariants suffice to establish the property we care about. However, it might be that these conditions don't fall within decidable logic. IV actually allows some quantifier alternations, so long as the alternations don't form a cycle. I won't explain exactly what this means, but the important thing is that IV will produce an explanation if a cycle like this exists. These verification conditions are then passed to Z3, which determines whether they hold. The effect of decidability is that if a verification condition doesn't hold, Z3 will produce a concrete counterexample, which can explain the error in terms of a protocol trace. The result is that each step, the proof engineer gets useful information about what is going right or wrong in the proof. The approach I've described for the toy agreement protocol is exactly the approach we applied to the stellar consensus protocol. For SCP, the main difficulty was defining the meaning of a quorum in decidable logic. Remember in the toy consensus algorithm that we defined the notion of a quorum through this axiom, rather than defining it directly as a majority of nodes. That's because the definition of a majority involves both arithmetic and quantifier alternation, which means it doesn't fit into decidable logic. Fortunately, it's easy to see that any majority quorum will satisfy the axiom we chose, which makes this reasoning step sound. In SCP, the notion of a quorum emerges dynamically from the participants' trust relationships. That means we don't have such a simple notion of a quorum. We need to find out what properties of the quorum SCP relies on and try to specify them in decidable logic. This led us to a two-step verification process. First, we defined a set of axioms about quorums which were sufficient to prove the SCP protocol correct. And second, we built an Isabelle model of the protocol and proved all the axioms we rely on hold. This fits with our theme of using the right tool for the job. We did most of the verification in IV, which made the proof much more straightforward. But in order to apply IV, we had to prove a few tough theorems using Isabelle. In other words, we applied the more powerful but more expensive verification tool exactly when it was needed. Of course, this creates the possibility of a mistake in our proof. The property we proved in Isabelle might be different from the one that we rely on in IV. It's important to be aware of these assurance gaps, but in this case, there's such a close correspondence between the two theorems that we don't consider it a significant risk. For the stellar consensus protocol, we care about two properties. First, that two nodes that share sufficient trust relationship are guaranteed to come to the same decision. This is a safety property. Second, that two such nodes will eventually reach a decision, a liveness property. The approach I've described works great for safety properties, but liveness properties are generally the most difficult ones to prove. Fortunately, it turns out that many liveness properties can be transformed into safety properties automatically. This is exactly what we did with SCP. The liveness properties are expressed in linear temporal logic and are converted into verification conditions in a transition system and safety property written in decidable logic. Doing this preserves some of the good qualities of IV verification. If the liveness property doesn't hold, we get back an explanation, either a counterexample or a quantifier cycle. However, this transformation makes it much more difficult to diagnose errors, because it creates a significant gap between the property statement and the explanation. Using IV and the liveness to safety reduction made it possible to prove the SCP liveness properties, but there's much more research to do before liveness proofs in IV are easy. To me, formal methods are tools to help human experts build reliable systems. The long history of distributed protocol design shows that human insights fail when we try to understand the properties of these protocols. That's why we need tools like Ivy that are designed to help proof engineers be productive. The model of SCP we built for the Stellar Foundation consisted of just 150 lines of Ivy code. That was compact enough that the protocol designers could audit the design and ensure that we got it right. Proving the safety property required about a dozen invariants, which again is small and simple enough that we can engage with the protocol designers to understand the properties we need. However, as I mentioned above, liveness was significantly more complex. To prove this, we needed approximately 50 invariants. Writing these took about a month full-time once we understood the property. If you're interested in learning more about our proofs, we have a short paper at the FMBC workshop this year, and all our proof scripts are open source. Formal methods aren't a silver bullet, but they are a powerful tool for increasing confidence in a system. Day by day, we're seeing more evidence of how useful they can be at all scales of software engineering. To me, our project with Stellar represents a significant success for formal methods. So far as we're aware, this is the first consensus protocol of its type in deployment where both safety and LTL liveness properties have been formally verified. That's a great result, especially given the modest amount of effort it took to develop these proofs. I've said a lot of positive things about IV in this talk, but it isn't the answer for every assurance problem. Instead, IV represents a particular set of trade-offs that work well for distributed protocols. I take IV as inspiration for what can be achieved when we pick the right tool for the job. Thanks very much for listening to this talk.